Good morning, students. Am I audible? Am I audible? Rohit, Deepak, Jason, are you there? Am I audible? Abrisha, my voice is clear? Okay. Okay, I'll share my screen. Let me know if it is visible or not. Okay. So today we'll see about slope deflection method. Then we'll discuss this double integration method also. Okay. And in the next week, there will be doubt clearing classes. So if you have any doubts, you share in the class, then we'll discuss it. Okay.
Going to cover the double integration method in 4 parts. I start with a straightforward example in order to illustrate the basic steps. In part 1, I'm going to apply this method to a beam having a constant EI
Screen is
and a
visible?
continuous bending moment equation. In part 2, I'm going to show how to solve problems involving more than one bending moment equation. That is, how to handle beams having piecewise continuous bending moment. In part 3, I will consider a case where the beam is made of aluminum and steel, each having a unique modulus of elasticity. Finally, in part 4, I will show how a beam with a variable moment of inertia can
At
be
least
handled
respond
using
so
this
that I can
method.
move forward.
Part 1. Suppose we have a cantilever beam of length L subjected to a uniformly distributed load having a magnitude of W. We wish to write a deflection equation for the beam. Assume the beam has a constant modulus of elasticity E and moment of inertia I.
Okay. So let's
To
start
use
the
the
class.
double integration method, we must be able to write the bending moment equation for the beam algebraically. See lecture SA07 if you are not sure how to formulate such an equation. To come up with the necessary moment equation, I'm going to cut the beam like this. By behavior of structures, I mean how they displace and deform. Then I draw the free body diagram for the left segment. Finally, I sum the moments about the cut point to get my equation. Understanding of the behavior of structures contributes to the development moment equation is that shapes structural mx equals negative wx squared over 2. Focuses on a Note that this equation is valid for the entire beam. Shape of beams under applied loads. Let's start with a simple example. Here is a simply supported beam subjected to a downward load. Vx equals the double integral of m over
How
EI,
does the beam deflect?
I can write the deflection
Downward,
equation
right?
as
Like this.
Vx equals the double
Common
integral of
sense
negative
suggests
wx
that if you
squared
push on
over
a beam,
2
it bends
EI.
downward.
Okay,
What may not be
W,
intuitively
E, and
obvious,
I are
though, is how the
constants.
beam behaves at
So
the
let's
supports.
rewrite the
How does
equation
the
like
support
this.
restrict deformation? Let's examine the effect
Integrating
of a pin
x
or
squared
roller
once, I
support on
get
beam deformation.
Vx equals negative
If a
W
beam is
over
resting
2
on a pin
EI
or roller,
times the
then
integral of
support
1/3
prevents the
x
beam from
cubed
deflecting at
plus
the point of
C1.
contact. That is,
Integrating the
beam
expression
cannot
one
move
more
up or
time,
down
I
at that
get
point.
Vx
However,
equals
it
negative
can
W
rotate.
over 2 EI
As you can see
times
here,
1
the
over
beam
12
has
x
no
to the
vertical
power 4
deflection at
plus
joints A or
C1x
B where the
plus
supports are
C2.
located.
Note
But
that
both joints
C1
have
and
rotated.
C2 are the
Joint A
integration
has rotated
constants to be
clockwise,
determined
joint
using
B
the boundary
has rotated
conditions.
counterclockwise.
Since there are two integration
So a pin
constants, we
connection
need two
or a
boundary
roller.
conditions. The conditions are deflection at the fixed support is 0, and the
What
slope
about
of the
others?
elastic curve at the
Ashok
fixed
say
support
he is
is
saying
0.
that he can hear two voices. Okay. Okay. Let me
I know that the slope equation equals to the
try sharing
derivative
once
of
again. Let me share once again. Okay.
play. Deflection at the fixed support must be 0. That is L to the power of 4 divided by
Deflection
12
Is it
at the
fine
beam
now?
plus C1L plus
Developing a
C2
basic
equals 0.
understanding of how
Slope
structural
theta
systems
at L
behave under
equals
applied
0.
loads is an
Ashok,
important part
Mainam,
of
is it
structural
fine now?
engineering education.
That is L
By
cubed over
behavior of
3
structures,
plus
I mean how
C1
they
equals
displace
0.
and deform, and how
Solving these
stresses develop
equations
and
for
propagate
C1
in their
and C2,
members.
we get,
The ability to visualize or to have a qualitative
therefore,
understanding
the
of the
deflection
behavior of
equation for the
structures
entire beam can
contributes
be
to the
written
development
as
of an insight that
Vx
shapes
equals
structural
negative
engineering
W over
judgment.
24 EI
Okay,
times
let
x
me
to the
Lecture
power
let
of
me
focuses on a
4
share.
qualitative
minus
approach for
4L
drawing
cubed
the
x. L to the power 4 divided by 8 times EI. This was a straightforward application of the double integration method. Now, let's turn our attention to the more challenging
deflection
cases.
in beams. Developing a basic understanding of how structural systems behave under applied loads is an important part of structural engineering education. By behavior of structures, I mean how they displace and deform, and how stresses develop and propagate in their members. The ability to visualize or to have a qualitative understanding of the behavior of structures contributes to the development of an insight that shapes structural engineering judgment. This lecture focuses on a qualitative approach for drawing the deformed shape of beams under applied loads. Let's start with a simple example. Here is a simply supported beam subjected to a downward load. How does the beam deflect? Downward, right? Like this. Common sense suggests
Structural
that if we
systems
push on
are
a beam,
generally
it bends
subjected to
downward.
various
What may
loads.
not be
An
intuitively obvious,
applied
though,
load,
is how the
regardless
beam
of its
behaves at
source
the
or nature,
supports.
can be
How does the
classified as
support
either a
restrict
concentrated
deformation?
or a distributed load.
Let's examine the
For
effect of a
example,
pin or
in a
roller
bridge
support on
structure, a
beam
moving vehicle
deformation.
exerts a series
If
of
a beam is
concentrated
resting on a
loads on the
pin or
bridge girder.
roller, then the support prevents the beam from deflecting at the point of
The
contact.
weight of the girder
That is,
itself,
the
however,
beam cannot
is
move up
treated
or
as a
down at that
distributed
point.
load.
However, it
Further,
can
a
rotate.
distributed load can
As you
act
can
along
see
a
here,
line
the
or
beam
on a
has no
surface.
vertical
That is,
deflection at
we
joints
have
A or B
one-dimensional
where the
distributed
supports are
loads
located,
and
but both
two-dimensional
joints have
distributed
rotated.
loads.
Joint A
A
has
load
rotated
distributed over a
clockwise, joint
surface,
B
such as a
has
floor
rotated
system, is
counterclockwise.
considered two-dimensional.
So a pin connection or a roller connection prevents deflection but allows rotation in beams. How about a fixed support? How does it affect beam deformation?
A load distributed along the
A
length
fixed
of a
support
beam
prevents
is
both
considered
deflection and
one-dimensional.
rotation at the point of contact. Here is a cantilever beam with a fixed support at
In
A.
this lecture, we're
The
going to
beam
examine
bends
the
downward,
analysis of
but
beams
at A it
subjected to
remains
various
horizontal.
one-dimensional
That is,
distributed
the beam
loads.
neither deflects
We
nor
could
rotates
have
at a fixed
a
support.
uniformly distributed load, this is a constant load, the load
Here is
magnitude does
another
not
example.
change over the length of the beam.
The beam rests
A
on a roller
triangular
support
load,
at the left end
in this case the
and is
load
fixed at the
magnitude
right end.
changes linearly
How
with
should
a
we draw
constant
the
slope.
deformed shape of the beam?
A
Here's
trapezoidal
what we
load.
know.
This
The
load can be
beam has a
viewed as a
general
linear
downward
combination
deflection
of a
away from the
uniformly
supports.
distributed
At
load
A, the
and a
beam has no
triangular load.
deflection, but it rotates.
A double
At B,
triangular
there is
load,
neither a deflection nor a rotation. Here is the deformed shape that satisfies these constraints.
or a generalized distributed load where the
As you
load
can see-
magnitude is defined using an algebraic function.
So here, I guess this is the
For our
second time I'm
purposes in
repeating
this
this
lecture,
class.
beam
So
analysis
see, slope
involves
deflection
calculating
means
support
why
reactions.
it is necessary. So when you apply a lateral load over the structure of your
And the
beam, then
internal forces.
over the whole structure of the building, then it will affect these beams.
How
Okay,
do
the
we
beam
handle these
spans. So
calculations
it
when
will
the beam is
deflect in
subjected to a distributed
in this
load?
way. Suppose
For
this is your
calculating support
beam
reactions,
span
we can replace
of
the
a building.
distributed load
So it
with
will
a
deflect like
concentrated load
this. So
before
how much is the
formulating the
deflection? So we
equilibrium
should
equations.
avoid the minimum
For
deflections.
determining the
So we should avoid
internal
these
shear and
deflections. So
moment
there should be some
forces,
minimum
however,
value.
we should
That's
not
why the
replace the
need of this
distributed load with its
topic slope
equivalent
deflection. How
concentrated
much it
load.
will give this
If we do,
slope
less than
and
accurate
deflection.
results will be
Okay.
obtained. So let's examine
So this
each
is a
type of
support
calculation
given.
separately.
Up
First,
or downward
let's see
movement
how
it will be.
support reactions can
Rotation
be
is permitted
calculated when the distributed
at
load
these
is present.
supports.
To
It
determine the
will give us
support
clockwise
reactions, we
movement.
start by
Rotation it
replacing the
will give
distributed
us
load with a
counterclockwise rotation.
concentrated load
By
called the
supports, what we do,
equivalent
we
concentrated load. Note that a distributed load defines a geometric area. For example, in the case that the load is distributed uniformly over the length of the beam, the load forms a
for
rectangle. Here, the base of
different
the
condition,
rectangle
different
is the
support
length of the
condition
beam,
used to
and the height of the rectangle
support this
represents the load magnitude.
spans.
Since the
Okay.
load magnitude is
Suppose a
given as
cantilever beam,
force
so this will
applied by
deflect in
unit
this way.
length,
Let me
then
note.
the area of the rectangle,
This beam will
base
deflect
times
in
height,
this
gives
way.
the total load
This way.
applied to the
So
beam,
here
as
there
if
will
the
be zero
distributed
slope and
is
zero
condensed
moment, but
into a
here
single
it will
point
have
load.
some slope and
The value of
deflections.
the
Okay.
total load is indeed the magnitude of the equivalent
Support.
concentrated
Okay.
load.
So no deflection
But if we were to
at
replace the
A point
distributed
because it is a
load with its
fixed point,
equivalent
and the B
concentrated
point
load,
is free,
where on the
so there
beam
will be
would we
some
place the
deflections.
concentrated load?
So
The
when you are
location of the
given a
concentrated
cantilever
load is
beam
the
with
geometric
some
center
support,
of
so
the
this is
area
called
formed
as
by the
prop cantilever.
distributed load.
Okay.
In
When
this case,
a
we know
cantilever
that the
beam is
center of the
given, suppose
rectangular load
one end
is
is fixed,
located
another
at the
end is free. So this
midpoint of
is
the beam.
cantilevered.
So
But
that
when
is
you
where we
provide
place
a
the
support
equivalent
here,
concentrated
any
load.
kind of support, so this beam
Now we're
becomes
ready to
prop
calculate the
cantilever.
beam's support
Okay.
reactions by formulating the equilibrium equations and solving them for the unknowns.
So it will have no deflection at this because this support is restraining the deflection. So you will
Here
have
are a
no
few
deflection at this
examples
position.
illustrating this process.
Here also no deflection, no rotation. Here,
Example 1.
as this is
A
fixed, so
beam is
here there will be
subjected
no
to a
deflection, no
uniformly
rotation.
distributed load
As
of
this
2
is
kilonewtons per
it
meter.
is not fixed,
What
just
are
the
the
support,
support reactions?
roller support.
The
So
beam is 10
it will
meters
resist
long.
the deflection, but there will be some
First,
rotation.
let's replace
Okay.
the distributed load
Now
with
in
a
this kind of beam,
concentrated
there
load.
will be downward deflection.
The magnitude of the equivalent
This
concentrated
is a
load equals to the
curve.
area of the
This is
rectangle
also this
defined by
dotted
the
line is also
distributed
called
load.
as elastic curve.
The
Okay, this is
rectangle
a
has a
deflected
base
shape.
of 10 and a height of 2,
No
so its
deflection at
area
this.
is 10 times 2 or 20. Note that the unit of this
Okay,
force
so this is a kind of
kilonewton.
beam cantilever,
The
but
equivalent
this
concentrated
AB
load
part,
is
this is
placed at the
prop
center of the
cantilever, but AB
rectangle,
part is
which is 5
little
meters away from the
overhanged.
left
Okay,
end of the beam.
so in
As I mentioned before,
at this
the
see,
support
there will be no
reactions of a
deflection,
beam
no
subjected to
rotation.
the uniformly
Deflection will be in
distributed
this
load are the
beam,
same as
and
the
there will
reactions
be
of a
clockwise
beam
rotation of
subjected
this.
to the equivalent
Okay,
concentrated
so
load.
let's say continue.
So to find the reactions, we can use the beam
no
subject to the
deflection at B.
concentrated load.
Therefore,
Here is
in
the
the
free body
absence of any
diagram
loads
of the
applied
beam.
to segment AB,
The
the beam is
reactions are
going to
determined
deflect
by
like
formulating and solving the
Zero
equilibrium
deflection and
equations for the
rotation at
unknown
C.
forces.
Downward deflection in BC. The deflection starts decreasing past the point of maximum, going back to 0 at B, where the beam is forced to turn clockwise.
Example
Since
2.
there is no
This
load
beam
pushing
is
down on
subjected
segment
to a
AB,
triangular
the segment
distributed load.
deflects upward
Determine
following
the
the
support
direction
reactions
established
for
at
the
B.
beam. The magnitude of the equivalent
Here are a
concentrated
few
load
more
equals to
examples
the area of
illustrating
the
the
triangle
process of drawing the
defined by the
deflected
load.
shape of beams.
The triangle has a base
Here,
of
the beam
12 and a
deflects
height
downward
of
under
2,
the load in
so
between
we
the
can write
supports.
P equals
Consequently,
12
there is a
times
clockwise
2
rotation,
over 2,
but no
or
deflection at
12
the left support,
kilonewtons.
and a
The
counterclockwise
equivalent
rotation with
concentrated
no
load is
deflection
placed
at
at
the
the
right
geometric
support.
center of the
Since the beam is
triangle,
not
which is
restrained
located
at A,
at
and segment
1/3
AB
of the
is not
away
subjected
out of the
to
right
any
angle
loads,
along
the
the
segment
base.
deflects upward.
Therefore, the concentrated
Similarly,
load needs
segment
to be
CD
placed
is
4
forced to
meters
move
away
upward
from
as
point
shown.
B. The support reactions for the beam subjected to the uniformly distributed load are identical to the reactions of the beam subjected to the equivalent concentrated load.
In this
To
beam,
find
the
the
middle
support
segment behaves
reactions, we can
similarly
use
to
the
the
beam
previous
subjects to the
example. The
concentrated
beam
load.
deflects down
Here
in
is the
segment
beam's
BC
free
with a
body
clockwise
diagram.
rotation at B
We then
and a
calculate the
counterclockwise
reactions by
rotation at C.
formulating and
But
solving
since
the
there is a pin
equilibrium
at A,
equations
the
for the
deformation
unknown
curve needs
forces.
to return to A. This forces segment AB to deflect upward. Similarly, the beam has a zero deflection at D.
Example
Therefore,
3.
the beam needs
In
to
this
deform
example, we wish to
upward in
determine
segment
the support
CD,
reactions
like
of a
this.
beam when it's subjected to a trapezoidal load. To find the magnitude of the equivalent
This beam
concentrated
is
load,
similar to
we
the
need
beam
to
in the
calculate
previous
the area
example.
of the
Here,
trapezoid.
however, there is a
This
fixed
equals to
support
the
at the
sum
right
of the
end
two
of the beam.
sides times
The
half of the
beam
base of the
deflects
trapezoid,
downward in
that
segment
is,
AB
area
with a
equals
clockwise
1
rotation
plus
at
3
A and a
times 12
counterclockwise
over
rotation at
2,
B.
or
The
24.
rotation at B forces the
The
beam to
location of the
deflect upward
equivalent
in segment
concentrated load
BC,
is the
which in turn
geometric
causes
center
the
of
beam
the
to
area,
rotate
which can be
clockwise
written
at C.
as
Consequently, the beam deflects downward in segment
x
CD with a
equals
zero
L
rotation
over
at D.
2 plus L over 6 times B minus A
This beam
over
deflects
B
downward,
plus A.
but the deflection curve,
Since
also
L is
called the
12,
elastic curve,
A
has a
is
zero
1,
slope
and
at
B
A
is
and
3,
B.
we get x equals 7. That is, the geometric center of the trapezoid is 7 meters away from the left end of the beam.
The elastic
So
curve
here is
for
the
this
free
beam
body
has a
diagram
zero
of the
slope
beam
at
when the
A, a
distributed
negative
load
slope
is
at
replaced
B,
with
and
its
a positive
equivalent
one at C.
concentrated load.
So the elastic
We
curve
can
looks
now
like
write
this.
the equilibrium equations and solve them for the unknown reactions.
Finally, the elastic curve for this beam looks like this.
An alternative formulation for this problem involves decomposing the trapezoidal load into a rectangular load and a triangular one, such as if we add the triangle to the rectangle, we get the trapezoid.
There are
We can
times,
then
however,
replace
that
each
the overall
distributed
shape of
load
the
with its
elastic
equivalent
curve is not
concentrated load.
intuitively obvious.
The rectangular
For
load
example,
has an equivalent
consider a beam
concentrated
subjected
load
to a
of 12
concentrated moment, as
kilonewtons
shown
placed
here.
at the center of the beam.
You
The
may not be
triangular
able to
load has
figure
an
out how the
equivalent
beam deflects
concentrated
by
load
visual
of 12
inspection. In
kilonewtons
this
as
case,
well.
we can use the
This load
relationship
is
between
placed at the
bending moment
geometric
and
center of the
deformation in the
triangle,
beam
which
to
is
draw the
located
elastic
8
curve.
meters away from the left
By
end of the
convention,
beam.
we know that a positive
Here are
moment
the
in the beam
equilibrium
causes a
equations based for
concave
this
up
alternative
deflection like this.
formulation. Obviously, they
And
produce
the
the
beam
same support
deflects down
reactions
when
as the
bending moment
original
is negative,
formulation.
like this. So if we know how
Example
bending
4.
moment varies in the beam,
In this
we
problem,
can
the beam
determine
is
the shape of the
subjected to a
elastic
parabolic
curve.
load defined
For this
using the
beam, we
quadratic
know that the
equation
left reaction is downward
Wx
with a
equals
magnitude of
2
m over
minus
L,
2 over
and the right reaction
25
is upward,
times
having a
x
magnitude
minus
of m
5
over L.
squared.
So the
To find the
moment in the left
magnitude of the
segment is
equivalent
linear,
concentrated
negative,
load,
and
we
decreasing
need to
in
determine
magnitude,
the area
like
under
this.
the curve. This can be done by
Since there is a
integrating
clockwise
Wx.
concentrated
The
moment at the
area
midpoint
is
of the beam,
40
there's
over
going to be a
3.
jump in the
To
moment
find the
value from
location of the
negative m over
equivalent
2 to
concentrated load,
positive m
we
over
need to
2.
determine the
The amount of
location
the
of the
jump is
geometric
equal to the
center of the
magnitude of the
area.
concentrated
This
moment.
is done using
Therefore,
this
bending
equation.
moment in the right half of the beam is linear, positive, and decreasing, as shown here.
So the center of the area is
Now we
located
should
at
be
the
able to draw
midpoint
the
of the
elastic
beam,
curve
5
using the
meters away
information
from
embodied
point
in the
A.
moment diagram.
Here is
The
the
beam
free body
bends
diagram
concave
of the
down in
beam,
the left
where
half,
the
since
distributed
moment
load
is
has been
negative there,
replaced by its
but the right
equivalent
half of the
concentrated
beam
load.
bends up, like this,
The equilibrium
since moment is
equations and the
positive
support
there.
reactions are.
Putting these two pieces together, we end up with the entire elastic curve for the beam. As our last example, let's draw the elastic curve for this beam. I'm going to use the beam's moment diagram to help figure out the overall shape of the elastic curve. First, let's calculate the support reactions. Now, draw the shear and moment diagrams. If you are not sure how this is done without formulating the shear
conjugate
and
beam
moment
method.
equations, see lecture
How would you go about
SA09.
determining the deflection
Note
in
that
a
the moment
beam at an
diagram has a
arbitrary
positive
point?
region and a negative
Say
region.
deflection at point
Therefore,
C
the beam
in
is
this
going
beam.
to deflect down in
One
the
approach
positive
is to
region,
first
like
derive
this.
an equation for deflection, and then
And it's going to
evaluate it
deflect
at the
up
point
in
of
the
interest.
negative region, like this.
The double integration method, discussed in previous
Now, putting the
lectures,
two
is an
parts
example
together,
of this
we
approach.
get this.
Another approach entails calculating deflection
Keep in
at the
mind that
desired
this is an
point,
exaggerated
without
shape
needing
of
to
the
write
elastic
an
curve,
explicit
and the drawing
equation for
is not to
deflection.
scale. Yet,
The
the drawing
conjugate
helps
beam
us better
method is an
understand
example
how the
of this
beam
approach.
behaves and deforms
This
under the
lecture
applied
presents
loads.
and illustrates conjugate beam method for calculating deflection in simply supported beams.
To start, let's
So this was the overview of slope and deflection method. Okay, let's move to, as we discussed in earlier classes, double integration method, movement area method. There were 5 methods to solve the deflection and beams, right? Let's see another session for double integration method. Okay.
to the double integral of Wx, since Vx is defined as the integral of Wx. So if we express the applied load as a
Deflection in
mathematical
beams.
function,
The double
its first
integration method.
integral describes shear in the beam.
In this lecture, we are
and the
going to
function's
examine a
second
mathematical
integral
basis for
describes
calculating
moment
deflection in
the beam.
beams. By
That
the
is,
end of the
this is a
lecture,
graphical
given a beam, you would
representation
know
of
how to
the
formulate
integral
an
of
algebraic equation
Wx.
for representing
And
its
this
deflection.
is a graphical representation of the
Here
double
is a beam,
integral of
and
Wx.
here is its elastic curve.
But what does
Let's
all
refer
this
to
have
the
to do
beam's
with
deflection as
calculating
V.
deflection?
Note
We're
that
going
V
to use
varies
the
with X.
relationship between load,
V is
shear,
0
and
at the
moment
beam's
as a
ends,
template
but
for
it changes
calculating
value in
slope
between the
and
ends.
deflection.
We
Let's
wish to
see
come
how.
up with an algebraic equation that enables us to calculate V at an arbitrary point X.
Slope in a beam
To get our
can be
equation,
defined
we
as the
start by
integral
drawing
of
a
m
tangent
over
line
EI,
to the elastic
where
curve
m
at
is
an
bending
arbitrary
moment.
point. Let's denote the angle that
V
the
is
tangent
modulus
line
of
makes with the
elasticity,
x-axis by theta.
and
That
I
is,
is
tangent
moment of
theta
inertia,
is the change
and
in
deflection is
deflection,
defined as the
dv,
integral of
with
slope,
respect
or the
to
double
change in
integral of
x,
m over EI.
dx.
See lecture SA12
Let's make a
if you would like
simplification
to know
here.
why these
Since a
equations
beam's
hold
deflection
true.
is relatively
Note the
small compared to the beam's length,
these
then theta is
equations
a
and
relatively
these
small
equations.
angle. Therefore,
Here,
we
if we
can
view
equate
m
tangent of
over
theta to
EI
the
as a
angle itself.
continuous load
That
applied
is,
to a
if
beam,
theta is
then
given in
theta
radians, we
represents
can
shear
write
in the
theta
beam,
equals
and
tangent
y
theta.
represents moment in the
But
beam.
is this a reasonable approximation? Let's put it to the test.
Let me restate
Say
what I just
theta is
said.
10 degrees.
If we draw
In
the moment
radians, this is
diagram
equal
for the
to
real
pi
beam,
over 18, or 0.175.
divide the
Tangent
diagram
of 10
by EI
degrees
to get
is
what is known as m over
0.176.
EI diagram,
As you
and
can
treat this
see, the two
diagram
numbers
as a
are almost
distributed load
identical.
placed on a beam
So
similar
this
to the real
simplification
beam.
is okay. We can write theta equals tangent theta
Then
equals
shear in that
dv
beam corresponds
dx,
to the slope of the
or
elastic curve.
dv equals theta times dx. Integrating
And
both
bending
sides of
moment
this
in that
equation,
beam
we get
corresponds to the real
v
beam's
equals
deflection.
integral of theta dx. Now, to actually come up with an algebraic
Here is a quick
equation for
overview of
v,
these steps.
we need to integrate the right-hand side
Suppose
of the
we wish
equation.
to determine this
To
beam's
do so,
deflection
we
under
need to
the applied
represent theta in
concentrated
terms of
load at
x.
point C.
But how?
The beam has a constant
This can be done
EI.
by expressing theta in
We
terms
start
of
by
bending
drawing the
moment
beam's
in the
moment
beam.
diagram.
And since we know how to express
Divide the
bending
moment
moment in
diagram
terms of
by
x,
EI,
then we can
forming the
easily
m over
calculate the
EI
integral
diagram.
of theta dx.
Now, draw
So,
what is called the
let's see
conjugate
how we
beam.
can relate
I will
theta to
explain how the
bending moment,
conjugate beam
m.
may differ from the real beam
When a
in a
beam
minute.
deflects
For
like
this
this,
problem, the
its top
conjugate
fiber
beam
is
is the same
compressed
as the
and the
real
bottom
beam.
fiber is stretched.
Place the m
To be
over
more
EI
precise,
diagram
it is
on the
not just the
conjugate
outer
beam as
fibers
applied
that
load.
change length,
Then,
but
determine
almost
the
all the
bending moment
fibers in the
at
beam
point
change
C in
length.
the conjugate beam.
The top part of the beam goes under compression. Its fibers shorten. The amount of compression, however,
This
varies
is
from
the
fiber to
deflection in
fiber.
the real beam
The
at
outer
point C.
fibers are compressed
Before
more
we
than
look
the
at a
inner
few more
ones.
examples,
For
let's see
example,
how the conjugate
fibers on
beam could
plane
vary
A
from the
are
real beam.
compressed more than fibers on plane B.
The conjugate
Similarly,
beam
the
has
bottom
the
part of
same
the
length
beam
as
undergoes
the real
tension,
beam
and its fibers
always.
stretch.
The supports
But
for
the
the
outer
conjugate
fibers are
beam,
stretched
however,
more than the
could
inner
be
ones.
different than
The
those
closer
in the
we get to
real
the
beam.
inner core of the beam,
If
the
there
less
is a fixed
compression or
support at
tension
either
takes
end of
place.
the real beam,
In fact,
we
there
need
is
to
a
turn it
surface
into a
inside the
free
beam on which
end in the
fibers do not
conjugate
change
beam.
length.
Why?
The fibers are
Keeping
neither
in mind that
compressed nor
shear in the
stretched.
conjugate beam
In effect,
represents
this surface
slope of the
separates the
elastic
compression
curve
zone
in the
from the
real
tension
beam,
zone.
and
We
moment
call
in the
it the neutral
conjugate beam
surface.
represents
In the two-dimensional
deflection in
view
the
of the
real
beam,
beam,
we call
then
it the
shear
neutral
and moment
axis.
at the boundaries
So,
of the
when a beam
conjugate beam
bends, all its
must
fibers
match
change length,
slope and
except for the
deflection
fibers
at the
along the
boundaries
neutral
of the
axis.
real beam.
This fact helps
Since
us
slope and
establish a
deflection
simple
at the fixed
mathematical
end of a
relationship
real
between the
beam are
slope of the
zero,
elastic
then
curve
shear
and
and
the
moment
geometry
at
of the
that end
deformed
in the
beam.
conjugate beam
Let's see
must
how.
also be zero.
Consider
The
a
only
very
end
thin
condition
slice
that
of the beam.
produces zero
The width of the
shear
slice
and
is
zero
denoted by
moment is a
dx.
free end. That is,
When the
there
beam
is no
bends,
shear
this
or
slice
moment
deforms
at
like
the free
this.
end of the beam.
Let's refer to
Therefore,
the
the
arc length
conjugate
along the
beam
neutral
must
axis
have a
of the
free
slice as
end where the
ds.
real beam
This
is
arc
fixed.
length can be assumed to be that of a
What if the
circle
real
having a
beam
radius of
has a
r.
free end?
We refer to
What would be
r
the
as the radius of
corresponding
curvature.
support in the
Then
conjugate
we can
beam?
write angle
The
d
free end in
theta
the
times
real
r
beam
equals
becomes a
ds.
fixed support in
By
the
the way,
conjugate beam.
d theta is the
Why?
difference
Because
between
the
theta
real
1
beam
and
has
theta
a
2,
non-zero
where theta
slope
1
and
is
a
the tangent
non-zero
angle of the
deflection
left end
at
of the
the free
slice,
end.
and theta
Therefore, the
2 is the
conjugate
tangent
beam
angle
must
at the
have
right
a
end of the slice.
non-zero shear
Let's
and a
rewrite this
non-zero
equation
moment at
as
the
d
point.
theta
The only support
ds
type that
equals
produces
1
a
over r.
non-zero shear and
Also,
moment
let's make
is
another
a fixed
simplification.
support.
Since ds is the
What if
unchanged
the
length
real
of the
beam
segment
rests
along the
on a
neutral
pin or a
axis,
roller?
we can
What would
replace
be
it
the
with
corresponding
dx.
support
So
type in
we
the
can write
conjugate
d
beam?
theta dx
Well,
equals
that
1 over
depends on the
r,
location
or
of the
d
support.
theta equals 1 over
If the
r
pin or the
dx.
roller is an
Integrating
end
both sides of
support,
the
then the
equation, we get
corresponding
theta
support in the
equals
conjugate
integral
Anyone left to write their roll number? Last roll Mero 041. Okay, I'm ending. Write your roll numbers, okay? Then I'll end the class. If anyone left to write the roll number, please write your roll number. And if you want any topic you want me to discuss, type in the chat box. I'll discuss that in the next classes, from next classes. Okay. Okay, hope everyone wrote, ma'am. Okay. Hope everyone wrote their roll number. Okay, so I'm ending this class. And if you want me any topic you want to discuss, so send it to CR and CR text me on the WhatsApp. Okay, I'll discuss from the next classes, and I'll discuss some numericals also. Okay, so thank you. I'm ending this class. Okay.